So before we talk about ion beam fabrication, so first we want to talk about imaging using focused ion beam. So we know that for the focused ion beam, focused ion beam, so it also generates secondary ions and secondary electrons. So those signals can be used for the imaging purpose. But it's very different from electron beam imaging in that, first, FIB imaging is destructive. For example, if you have the structure here, this is the structure before imaging. So after 1 minute imaging, because the ion beam can sputter away the material, so the material gets damaged. As a result, for the ion beam imaging, so you have to do it very fast, or you have to use very low current to minimize the damage by the ion beam. So we can take the secondary electrons or secondary ions for the imaging purpose. For example, if we want to do the imaging using secondary electrons, this is the most popular. So we need to bias the detector. So the detector should be biased positive to attract those negatively charged electrons. So the electrons is emitted from the top 5 to 10 nanometer. So this is the same case for the SEM. What did you see here? The drawing is not so so good. So we have the 20 keV electron beam. So even though the electron can go to pretty deep, but only the very top surface, only the very top 5 to 10 nanometer electrons can come out. So the deeper you set, the secondary electrons cannot come out. So it's the same thing, the same 5 to 10 nanometer for the ion beam or for the electron beam. So normally we use 30 keV to have very good current, have very good focus, and 40 picoampere current. If the current, as I said, if the current is higher, you get higher signal, but you got more damage. So usually we use a 40 picoampere current. So ground in the metals is very bright, so oxide is dark. So why oxide is dark? So this is because of the charging effect. If we draw it here, so here you have the oxide, so the silicon dioxide. So when the ion beam comes in, so we have the gallium ion beam. So the gallium ion beam is positively charged. So as a result, the substrate will be positively charged. Then the signal electrons, so the electrons, the secondary electrons, this one will be pulled back. So this negatively charged electrons will be pulled back by this positive charge. As a result, the oxide will be dark. So we can also do the imaging using secondary ions. So for the secondary, this one is positively charged, so the detector needs to be negatively biased. So because this is like an atom, much bigger than the electrons. So only the very top surface, atom can be kicked out. So it is very sensitive to the top surface. It's sensitive to the top 0.5 nanometer to 1 nanometer. So here the oxide will be brighter because again the substrate is positively charged. This one is also positively charged. So this positive charge will help this positive charge to come out to go to the detector. So the yield is low. The yield is very low. So the imaging will be lot of noisy. So besides normal imaging, so we can also do the ion channeling contrast. We will see this one later on, as well as material contrast and the voltage contrast. So the voltage contrast is nothing but a charging effect. It's similar to what we have seen for the electron beam, is the charging effect. So we have the charge, you have voltage, so you form some contrast. So here is the image for the ion beam. So we have ion beam coming in. So this one we detect secondary electrons. This one we detect secondary ions. So you can see they are not the same. This one is bright, but this one we see something dark. So why they look different? So this is because for the ion beam, for the ion secondary ion mode, it's very sensitive to the top 1 nanometer. If you have some contaminant, like a layer of oil molecule, organic contaminant, this will make big difference. As a result, it become the contrast is different. This one 5 to 10 nanometer is less sensitive to the surface contaminant. Okay, the material contrast. So we know that for the case of SEM imaging, this one is the yield of the secondary electrons. So for the SEM imaging, you can see the higher atomic number, the higher the yield of the secondary electrons, as you can see here. And from this image, you can roughly see that this metal here, this one is higher atomic number than the material surrounding it. But when we have the ion beam, this solid curve, we have the 30 keV gallium ion. This one is the yield of the secondary electrons. You can see overall it is the opposite. The higher atomic number, the lower the yield of the secondary electrons. In addition, we have some fine changes along different materials. So here is the secondary ion microscopy. It also takes secondary electron for the imaging purpose, for the image. Here we have gallium ion. You can see here, for example, this part is really dark. This is very dark, but this part is bright. It's bright. Because of the contrast, you can see this part may be lower atomic number, so it's dark for the electron SEM imaging, but for the lower atomic number, it is more signal, so it's bright for the ion beam imaging. So now let's look at this one, a voltage contrast, the voltage contrast. You can see here. So actually the top, you can see the top and the bottom, so they have the same structure. So the difference is that the top part is isolated from outside. It's isolated. As a result, so the charge, when you do the imaging, so the gallium ion will be trapped on the top part. The charge cannot go away, so it's very dark. So this positive charge will pull back this negative charge electron, so the signal is very weak, it's very dark. But when you make the connection, when you make this metal connection, so that the charge on the top part can be dissipated to the other part. So there is no more charging, no more voltage. Then you see the signal, the top and the bottom looks the same. So this is the charging effect. So we can see something similar using SEM imaging as well. So now let's look at the third one, is the channeling effect, ion channeling. So I'm sure you have learned the ion channeling when you take the NE353, when you learn about ion implantation, there is also ion channeling effect. So here the idea is the same. So when you have the ion beam, when they are aligned along the crystal orientation, it penetrates much deeper than normal alignment. But when they penetrate very deep, it has smaller interaction. The smaller interaction, you have the lower Sebastian yield and also lower yield of the secondary electrons. So you can see here, this is the intensity of the secondary electrons. So when they are aligned, when the ion is aligned along the 001, 113, or 111 orientation, you get smaller signal. But you see the half angle, it's pretty wide. So this is not like a very, very narrow peak. It's a very broad peak. So that means you don't have to make the ion aligned perfectly. The ion don't have to be something like this. It's okay to have some collision. If I have collide this molecule, then bounce back, then collide with this atom, then go to collect this atom. But this is not a problem. It can still have the channeling effect, because when you have this kind of collision, so this is the glancing angle. So very large glancing angle. So we have this kind of very large glancing angle collision. It's pretty elastic. There is not much energy loss. So it still get channeled through, go to the very deep. So here's the result for the imaging purpose. So you can see here, on the right side it's dark, on the left side it's bright. Then you know this one is, you have the channeling effect. It's aligned with the channeling. This one, no channeling. As we see here. So we have the channeling, you get lower Sebastian yield and also lower yields of the secondary electron. So you get darker. The image becomes darker. So for the same material, this is the polycrystal material. You can see some area is dark, some area is black. It's white. So again, those dark areas, you have the channeling effect. Bright area has no channeling effect. So this effect can be utilized to study to analyze the green sets. So what you do, so you take the polycrystal sample, you do the imaging at one angle, then you rotate to the ion imaging again, then you rotate to the ion imaging. So in the end, you do some numerical fitting, then you can determine the crystal orientation of the material. This is the green side, and the crystal orientation. For example, this white color here, this may be 111 green, this may be 100 green, something like this. This is an easy way to analyze the green orientation, because there is no other way to. It's not easy to do this. If you do the accurate diffraction, can also tell you the crystal orientation. But accurate diffraction actually is normally not focused. You have the broad X-ray, so we have the polycrystal material. You get average, not focused. But using this method, you can analyze the green structure of the material. So now let's look at lithography. So lithography is using ion beam. So the ion beam can do more than electron beam. So for the case of electron beam, the only thing we can do is the exposure of the resist. We just do the E-beam lithography to do the exposure of the resist. For the ion beam, so we can do the same thing. We can write the pattern in the resist, similar to the electron beam lithography, because the ions can also generate secondary electrons. So the ion beam can also be used to expose the resist, and all the E-beam resist, all the electron beam resist can also be utilized as the ion beam lithography resist, because in the end, in both cases, it is the low energy secondary electrons that is mainly responsible for the exposure of the resist. So the main difference between ion beam and electron beam is that for the ion beam, so we have large momentum. You can sputter away the material. But for the electron beam, it's very difficult to sputter away the material. So for the ion beam, we can also use it to deposit the material locally. We will see this one later on. This is called ion beam induced deposition. So actually, we can also use electron beam. We can also use electron beam to deposit the material locally, but it is more popularly to use ion beam than using electron beam. And lastly, we can use ions to do the ion implantation. We have ion implanted into the substrate. It can be used as an action mask, or other purpose for the subsequent pattern transfer. So now we look at this one, ion beam exposure over the resist. So here is the comparison with the electron beam lithography and ion beam lithography using the resist. So first, the proximity effect for the ion beam is negligible. So we know that for the case of the electron beam, now here is the substrate. So electron come in, it goes very deep and go back scattered. You can see so also even very far away. This may be 10 micrometers from here. It can be exposed. This very large proximity effect. But we have the ion beam. So we have ion beam. Ion come in, stay here. It's very localized. It does not go far away. It's very localized. Only this small area get exposed. So we have much smaller proximity effect. But this is not good for the area exposure. So we want to expose a large area. For instance, if we want to expose this large area, if we use ion beam, so what do you have to do? So the pixel size, the beam spot size has to be similar to the pixel size. And that means if you expose one spot here, if another one, so they have to overlap. But we know that for the case of electron beam, they don't have to be overlap. For the electron beam, we can expose one spot here, another spot here, then another spot here. Oh. So one spot here, another spot. So the area in between, can be exposed by the proximity effect, because you can see the nearby area can be exposed by the scattered electrons. So this will make the exposure slower than electron beam, because the pixel size has to be small. Then the dwell time on each pixel will be very short. When it's very short, the machine may not follow. But because of the smaller interaction volume, so the resolution may be higher than electron beam because the interaction is very localized. Only you have a smaller ion range, a weaker scattering, lower energy of the secondary electrons with the smaller lateral diffusion. As a result, in principle, we have the same beam spot set. So ion beam can be a smaller feature set than electron beam because of the smaller interaction volume. So the sensitivity is much higher than electron beam lithography. So this can be higher not by a little bit, it can be higher by tens of times. So the reason is because so when we have the electron beam, so here is the resist. So on the top part, so here you have the resist. So most of the energy is deposited into the substrate. So here the substrate is not utilized. Only the top layer is the resist. But for the ion beam, all the energy is absorbed by the resist. As a result, it will generate more secondary electrons and is more efficient to expose the resist. So the energy they are not wasted, it's all absorbed by the resist. But it's more difficult to focus the ion beam because of the chromatic aberration. So we know that for the ion beam, this number is high, delta E. For the ion beam, this delta E number is high. So you have more energy spread, you have more chromatic aberration. So as a result, we have to use low beam current, smaller 50 picoampere for the high resolution. But we know that for the electron beam, we can use nanoampere beam current, or even tens of nanoampere beam current, we still get very good resolution. But this is not the case for the ion beam. So the ion will stay in the material to become an impurity in the resist. And the bigger the problem is the penetration depth. We know that for the 30 keV, so for the 30 kilo electron volt, ion beam, gallium ion, it will penetrate about 30 nanometer into a silicon. So we have the resist like a PMMA, it maybe go to 6 nanometer into PMMA. The 30 nanometer into silicon, 60 nanometer into PMMA resist. It's still very low. For the electron beam, we can penetrate easily a few micrometers. So because of this low penetration depth, so the resist PMMA has to be thinner than 60 or a few tens of nanometers. But this will make the lift-off or etching process difficult. The resist is too thin for the subsequent pattern transfer. So now let's look at ion beam milling. This one is much more important than the exposure of the resist. So the idea is very simple. If you want to make a structure like this, so what you do, you coat the film like a gold. You do the milling process, remove the material you don't want. You leave behind the material. So typically, one gallium ion of 30 keV can sputter away a few atoms of the silicon. If we do the calculation, we have 1 nanoampere beam current. Within 1 second, you can remove about 0.1 cubic micrometer. So the ion energy, as we said, is typically tens of kilo electron volt. Higher energy gives you more implantation. If you have even higher energy, higher than mega electron volt, there may be backscattering and also nuclear reaction. So usually for the case of the gallium ion beam, the energy is 30 keV. This is what we use. Here is the sputtering yield. The sputtering yield is defined as the number of the kicked out atoms per incident ion. So usually it's 1 to 50. That means one argon comes in, you get 1 to 50 atoms kicked out. So this is the sputtering yield. But this one this one should be for a heavier ion. For the case of gallium, I think the sputtering yield will not that high. So what do you see here? So this is the melting temperature. You can see the higher the melting temperature, the lower the sputtering yield. So from here you can see, for example, for the case of the gold. So gold has a low melting point, about 1,000 degrees, not very high. Then the sputtering yield, if the low melting point, sputtering yield will be higher. So why is you have this kind of melting point and sputtering yield, you have this kind of correlation? So this is because we have the lattice. You have the bonding energy. This is the bond. For the metal gold, you have metallic bond. For the dielectric materials like aluminum oxide, you have the covalent bond. So for the case of gold, we know gold is a noble metal. So we have the noble metal is pretty inert. So the bonding energy is very low. So we have very low bonding energy, it's easier get melted. So you have a higher melting point. It's very easy to get melted. We have low bonding energy, you get lower melting point. So when the bonding is lower, it's also easier to kick it out. It's easy to kick this one out. We have the higher sputtering yield. Now this bonding energy there is a term called a cohesive energy. So higher bonding energy is more difficult to melt, and also it's more difficult to sputter away. So lower sputtering yield, higher melting point. From here you can see that for the noble metal like gold, silver, those noble metals, they have a low melting point, they have high sputtering yield. So this is the 45 kilo electron volt krypton ion. You can see here, so gold, for this one, per nanocoulomb charge, of this krypton ion charge can move away 1.5 cubic micrometer. For the silicon, 0.27, or for all the other materials, they are smaller than gold. If you know the sputtering yield, you can calculate the sputtering rate. So the sputtering rate is given by the sputter yield, how many atoms kicked out per insulated ion, times the flux. The flux is the number of ions per second divided by the number density of the material. To get the flux, this is why you need to know it's related to the ion current. Related to ion current divided by E, right? This is ion current times 1 second, give you the charge divided by the E, you get the ion flux. For the number density, you need to know the density kilogram per mole. You need to know the density kilogram per cubic meter or kilogram per cubic centimeter. Then you also need to know the atomic weight, like how many gram per mole. You need to know how many gram per mole plus how many gram per cubic centimeter in order to get the number density of the material. But the actual mean rate is lower than what you calculate from this formula because of the reduplication. We will talk about reduplication later on. The reduplication is one of the major problems of the ion beam milling. Now here is the milling of the different materials with the fixed dose. The dose is 7.5 10 to the power 12 gallium ions. You can see the zinc has higher yield. Zinc has higher sputtering yield, it mills deeper. The copper yield is high, mills to this depth. So aluminum, silicon. So in this case, aluminum has higher yield than silicon. But from this chart, it looks like aluminum has lower yield than silicon. So maybe I think this because this is right for the krypton ion. So aluminum mills slower than silicon. But for the gallium ion, so the aluminum mills faster than silicon. So here you can see, for the silicon it's smooth, but for the copper the surface is really rough. So how come the surface is so rough? So this is because of the channeling effect. So when you have the green here, for example, along this green here, so the ion goes very deep inside. Because this green, the ion is aligned. So the ion is aligned along the single along a certain crystal orientation. So when the ion beam is aligned along certain crystalline orientation, we have this channeling effect. It goes very deep with low sputtering rate. This is the polycrystal material. We have made the steel, so you have the similar effect. It's very rough. So again, those areas here, you have the ion channeling effect. So the male rate is smaller. So how to get a smooth milling? So one way to do this is by doing the doping process. Doping. You can dope it. We have the dopant. The dopant will block the ion channels. As a result, you don't have the channeling effect. You get smooth bottom. So about 20 years ago, the European Union, they have a big funding program. They fund, I think, hundreds of million euros for the development of the nano FIB. So the goal of that funding is to replace electron beam lithography eventually with the ion beam lithography. But in the end, we know that for today, we still use more electron beam lithography than ion beam lithography. Nevertheless, they have the product. They have the product to do the lithography using focused ion beam by the company. The company is RIS. So this is the company. So in University of Waterloo, we have this nanofib that has the both gold ion and the silicon ion. So we have this nanofib at the University of Waterloo in the Water lab that has gold ion and silicon ion from this company, from the RIS. This is one of the outcome by this nano FIB European product. But they made 3 nanometer pulse by ion beam, so only 3 nanometer. So what you do, you have very thin membrane. When you have very thin membrane, you can make small. If the membrane is thick, it's very difficult to make this one. So what's the use of the 3 nanometer pulse? So this can be used for the DNA sequencing. So this can be used for DNA sequencing. So this nano pulse can be used for DNA sequencing. So we will look at DNA sequencing later on in the focused ion beam. So basically, you pass the DNA molecule through the nano pulse. So now let's look at the reseparation. As we have seen, the reseparation is a big problem. So when you mill the material, there will be a reseparation. For example, if you mill this part here, the material will be separated to the nearby area. So this is the reseparation. So this picture I take it from the internet. I take it from internet. But later on, if you think carefully, you will see that should not be reseparation here. There's no way for the material from here. So the material is bombarded away, and it will go away. No way to let it come back. So the drawing here is wrong. So there is no force to bring the material back. The gravity is very small. There is no electrostatic force. When we have this, the material bombarded away is neutral. There is no electrostatic force. So now let's look at the gravity. For example, so when you have the silicon here, one of the silicon atom is sputtered away with energy 1 electron volt. So this, you can see, is pretty low energy. But now let's look at if you have 1 electron volt, so how far it can go, so how high it can go. So this one you can calculate. It's not so hard. We have the formula: 1 electron volt equal to mgh. So E is, we know the charge, we know the G equals 9.8. This is the G is 9.8. H is the height we want to know. M is the silicon mass. So what is the mass of the silicon? We know for the silicon we have 28 grams per mole. So how can we know? How do I remember this 28 grams? So because for the silicon, atomic number is 14. For this, normally the number of the proton and number of the neutron is the same in the nuclear. So we have the 14 proton. There are also 14 neutron. So the totally we have 28. We have 28 proton or neutron. So that's why you get 28 gram per mole. So we know 28 gram per mole, we can calculate the mass of one single silicon atom. So you have 28 gram divided by Avogadro's number. And in the end, you get the height. The height, you get how much is the height? 350 kilometers. And even though 1 electron volt, it can go to 350 kilometers. So we can ignore the gravity. So this drawing, as I said, is rough. No material, no reseparation here. So because of the reseparation, I will mill the material from the right to the left, so you get the trouble. So how you do this? So you mill this line, so you mill like this. So you move from the right to the left. This is the scan direction. So when you move the material here, the material it got separated here. As a result, you see a slope. Because of the reseparation, you see a slope. The same thing is here. For this one, you mill center first. You mill from center, then mill to the edge. When you mill to the edge part, the material gets reseparated here. This one, you mill from the edge to the center, you get a shape like this. So now the question is, so how to attain, a flat bottom milling? So this one is done by a single pass. We move from the right to the left. So what you can do here, so this one you can see again, it's 2 seconds per line, single pass. So what you should do, multiple passes. So you mill something like this. So left to the right, then from the right to the left, you do this. We have 200 passes, then you get flat bottom. Now here's the summary for the ion beam milling process. So first, for the large and less critical patterns, we should mill it first using high beam current. When we have high beam current, the milling rate will be fast. We use multiple passes, not single passes, and we mill the fine and the critical patterns last. Using low current gives you higher resolution, and also multiple passes, always multiple passes. So now let's look at a single line milling. So what will happen? I will mill just one line. So first, we want to know what is the pixel spacing. So the line is milled by the pixel by pixel. It's milled pixel by pixel. But here is the pixel spacing. This is the beam diameter. So here is the beam diameter corresponds to about half. This is Gaussian beam. The width of the Gaussian beam defined as the beam diameter. So you can see here that normally the spacing cannot be too big. The rule is like the pixel spacing over beam diameter should be less than 1.5. For example, if you see here, when it's equal to the pixel spacing over beam diameter 1.5, you get smooth milling. When it's equal to 3, when the pixel spacing is 3 times of the beam diameter, you get this wavy milling, so not smooth line. If you mill a single line, this is the single pass milling of the line. You end up with always with the V-shaped. You always get this V-shaped channel profile. Why you got V-shaped? Because so when you mill very deep, you have not only the beam here. The beam looks like a cylinder, but actually look like a cylinder. Actually, you also have the beam tails. So this part of the beam, even though the current is low, if you mill a very long time, this part of the beam will mill away significant amount of the material. As a result, the opening will become, when you mill deeper and deeper, the opening here will also become wider and wider. So this one is ASU. This is the Arizona State University. They have the best electron microscope and ion microscope in the U.S. This university is similar to the McMaster University in Hamilton. The McMaster University in Canada, they also have the best electron microscope like SEM, TEM, FIB. So they have the best FIB. For example, we talk about plasma source FIB. So I think McMaster University is the only university in Canada that has the plasma source FIB that gives you much faster milling rate. At the University of Waterloo here, we get gallium ion FIB, and also we have the gold ion. We also have the silicon ion. The gold ion, as we know before, gold and silicon ion, this is one machine. You use gold silicon alloy to generate silicon ion and gold ion. For this example here, it is used by the arsenide ion. 90 keV, a pretty high energy. Current 5 picoampere, pixel spacing, this pixel spacing, the beam diameter 50 nanometer. You can see even very small beam current, you get the beam diameter is not small. So here we have this. So we have the beam tail milled with the material, and also we have the redeposition. When you mill the material here, it does not come out. There will be lots of redeposition on the side walls. This also make the shape like a V shape. So we see we have this V shape. Now how to mill a high aspect ratio? How to mill high aspect ratio narrow trenches? So the only way to get this one is to use a very low beam current. For example, here's the milling of the trenches with different beam current. We have 32 picoampere, you get this V-shaped. We have 3 picoampere, you get, it is also V-shaped, but this is very narrow. The same is here. Here the current is only 1.8 to 3 picoampere, a very, very low current, very well focused beam. You can have high aspect ratio milling. Thank you.